Our topic today is atomic structure from AS level chemistry. In O levels, we learned that atoms are the smallest particles which cannot be further divided. We learned that atoms contain a nucleus which comprises of protons and neutrons. Protons are positively charged, neutrons are neutral, and then around the nucleus, the protons and neutrons form the nucleus, and around the nucleus there are shells in which electrons orbit. Electrons have a negative charge. Now, in AS level chemistry, we learned that shells are further divided into subshells, and subshells are further divided into orbitals. Electrons are present in the orbitals, and each orbital contains 2 electrons. Now, we have 4 shells. There are K, L, M, and N. The first shell, that is K, has 2 electrons. These 2 electrons are contained in one orbital, which is called 1s. This can also be called a subshell and an orbital because it contains only 2 electrons. Now, the L shell has 8 electrons. These are contained in 2 subshells. The 2 subshells are 2s and 2p. The 2s subshell also acts as an orbital because again it has only 2 electrons. And the 2p subshell has 6 electrons. So that means that because each orbital contains 2 electrons, so the 2p subshell will have 3 orbitals. These 3 orbitals have their symbols, which are 2px, 2py, and 2pz. So the L shell has 2 subshells, 2s and 2p. 2s contains 2 electrons, 2p contains 3 orbitals, and each orbital contains 2 electrons. So 3 into 2 is 6. It contains 6 electrons. So 6 plus 2 is 8 electrons. Now the M shell contains 18 electrons. These are present in the 3s, 3p, and 3d orbitals. 3d subshell, sorry. 3s also acts as an orbital, as again it has only 2 electrons. 3p has 6 electrons, so therefore it has 3 orbitals. Those are 3px, 3py, and 3pz. Now the D subshell has 10 electrons, so therefore it has 5 orbitals. These 5 orbitals also have their symbols, but we don't have to learn them. So I'll just write that they have 10 electrons. So there are 2 electrons over here, 8 over here, sorry, 6 over here, and 10 in 3D. So they add up to 18 electrons. Now the next shell is N. N has 32 electrons. These are contained in 4 subshells. The first subshell is 4s. The second subshell is 4p. The third subshell is 4d, and the fourth subshell is 4f. Again, 4s has 2 electrons. 4p has 6 electrons, which are contained in 3 orbitals. Those are 4px, 4py, and 4pz. And then 4d has 10 electrons, and 4f has 14 electrons. Now, reviewing this once again, the first subshell has 2 electrons. It has 1 subshell, that is 1s, which can also be called an orbital as it has only 2 electrons. Now, 1 over here is represented by n, and n is a symbol for principal quantum number, which we'll do soon. So over here, the value of n is 2. And then in L, we have 8 electrons. Those are contained in 2s and 2p subshells. 2s has 2 electrons, 2p has 3 orbitals. Each orbital has 2 electrons. That makes 6. So 6 plus 2 is 8. Similarly, for M subshell, the principal quantum number is 3. It has 3 subshells, 3s, 3p, and 3d. 3s has 2 electrons. 3p has 3 orbitals. Each orbital has 2 electrons. So 3 2s are 6, 6 electrons. And then 3d has 5 orbitals. Each orbital has 2 electrons. So 5 2s are 10. So 10 plus 6 plus 2 is 18. And then for N, there are 4. The principal quantum number is 4. There are 4 subshells, 4s, 4p, 4d, 4f. 4s has 2 electrons, 4p has 6 electrons, 4d has 10 electrons, and 4f has 14 electrons. So over here, 4f will have 7 orbitals because each orbital will have 2 electrons. So 7 to the 14. Now the next thing is quantum numbers. So there are basically 4 types of quantum numbers. The first one is principal quantum numbers. Second is azimuthal quantum numbers, then magnetic and spin. Right now we'll do principal and azimuthal. The rest we'll discuss later. So what do quantum numbers, why do we need quantum numbers? Quantum numbers help us find the energy of a shell, the energy of a subshell, the orientation of the electron, and the movement of the electron. So right now we're discussing the energy of a shell, which is the principal quantum number, and the energy of a subshell, which is the azimuthal quantum number. So principal quantum number. Principal quantum number is represented by n. The values of n can be 1, 2, 3, 4 onwards. 1 is for K, 2 is for L, 3 is for M, and 4 is for N. These are the names of the shells that the principal quantum number represents. Now, the higher the value of N, the higher will be the energy of the shell. So N has the highest energy and K has the lowest energy. Now we have 2 formulas over here. The first formula gives us the total number of electrons in a shell. The formula for this is 2n squared. The second one is total number of orbitals in a shell. So the formula for this is 2n squared divided by 2 because each orbital has 2 electrons. So the number of orbitals will be half of the number of electrons. So we'll plug in the values of the shell into the formula to find the number of electrons in that shell or the number of orbitals. So for example, the first shell K has principal quantum number 1. So the number of electrons will be 2 times 1 square, which is 2, and the number of orbitals will be 1 as we did earlier. And then same for 2, 3, and 4. And I've shown that here. So for K shell, there are 2 electrons in the K shell and 1 orbital. In the L shell, there are 8 electrons and 4 orbitals. In the M shell, there are 18 electrons and 9 orbitals. And in the N shell, there are 32 electrons and 16 orbitals. So over here in K shell, there is 1 orbital, that is 1s. In L, there are 4 orbitals, that is 2s, and then 2px, 2py, 2pz. Similarly for M, there are 9 and then 16 for N. Next is the azimuthal quantum number. The azimuthal quantum number is represented by L. The values of the azimuthal quantum number, that is L, are 0, 1, 2, 3. And the azimuthal quantum numbers represent the energy of the subshell. So that's why 0 is for the S subshell, then 1 is for P, 2 is for D, and 3 is for F. Now, over here again, the higher the value of L, the greater will be the energy of the subshell. So F has the greatest energy and S has the least energy. Now, again, we have two formulas. The first formula is the total number of electrons in the subshell. So the formula for this is 2 times 2L plus 1. And then the second formula is for the total number of orbitals in the subshell. So again, over here, because each orbital has 2 electrons, so the number of orbitals will be half the number of electrons. So the formula is 2L plus 1. Now over here again, if we put the values of L into the formula, we'll get the number of electrons in the subshell or the number of orbitals. So over here in S, the number is 0. So S has 2 electrons, as we saw earlier, and then it has 1 orbital. P has 6 electrons and 3 orbitals. D, those 3 orbitals are Px, Py, Pz. And then D has 10 electrons and 5 orbitals, and F has 14 electrons and 7 orbitals. Now, next we'll do Aufbau's principle. So Aufbau's principle is also called the N plus L rule. According to Aufbau's principle, electrons fill first in the lowest energy orbital, and if two different orbitals have the same energy, then electrons first fill the orbital with the smaller value of n. Now, how to apply this? For example, we have the first two orbitals that are 1s and 2s. So for 1s, the value of n is 1. These are the values of n. These are the values of L. And then these will be the values of n plus L. So n plus L will give us the energy of the orbital. Now for 1s, the value of n is 1. And the value of s, the value of L for s orbital is 0. Similarly, for 2s, the value of n is 2. And then for s, the value is 0. So 1 plus 0 is 1. And 2 plus 0 is 2. So the lower energy is of the 1s orbital, which will be filled first, and then the 2s orbital. Similarly, the next one is 2s and 2p. Now, again over here, n, L, and n plus L. So n is 2 for both, which is the principal quantum number. The azimuthal quantum number for subshell S is 0, and for subshell P is 1. So 2 plus 0 is 2, 2 plus 1 is 3. Again, the 2s orbital will fill first, and then the 2p orbital. Now next is 2p and 3s. I'm directly writing the values of n, L, and then n plus L. So n is 2 for 2p, and then for p, L is 1. For 3s, n is 3, and s is 0. So when we add 2 plus 1, we'll get 3 for 2s and 3 for 3s as well. For 2p and 3s, we'll get 3 for both. So over here, in this case, as the energy is same, so what we learned earlier was that the electron first fills the orbital with the smaller value of n. So over here, the smaller value of n is of 2p. So the electron will first fill the 2p subshell and then the 3s subshell. Now in the next example, it's 3s and 3p. Again, the value of n for 3s is 3. The value of n for 3p is 3. The value of L for S subshell is 0. And the value of L for the P subshell is 1. So when we add them together, we get 3 and 4. So over here, it's clear that 3s has lower energy, so it will fill first and then 3p. Now, in 3p and 4s, the value of n is 3, which is the principal quantum number, and 4 for 4s. And then for p, the azimuthal quantum number, that is L, is 1, and it's 0 for 4s. So when we add them together, we get 4 and 4. Again, over here, both have the same energy, but electrons will first fill the 3p orbital because it has the lower value of n. Next is 4s and 3d. Over here, this is n is 4 for 4s and n is 3 for 3d. And then for s, L is 0, and for d, L is 2. So in this case, we're getting 4 and 5. Over here, 4s has lower energy than 3d. So what we have to remember is that 4s will fill first, and then the 3d subshell will start filling. And after 3d, there's 4p, and then that goes on. An easier way to remember which subshell fills first is, which orbital fills first. We'll write the subshells in this way, the orbitals in this way, 3s, 4s, 5s, 6s, and 7s. Now, when we come to p, keep reducing one from the top and one from the bottom. So we'll start with 2p, 3p, 4p, 5p, and we'll stop at 6p. Now, when we go to d, again, reduce one from the bottom and from the top. So we'll start with 3d, 4d, and 5d. And then when we go to f, so reduce one from the top and one from the bottom. So that is 4f. Now, which orbital will fill first? For that, the trick is that we'll draw diagonals and then we'll find the order. So the first diagonal is like this. So this is the order. First, there is 1s, then there is 2s, then 2p, then 3s, then 3p, then 4s, then 3d, then 4p, then 5s, and it goes on. So in the subshells, what is the maximum number of electrons? We've done that already. The maximum number of electrons in the S subshell is 2, and the P subshell is 6, the D is 10, and then 14 for F. The minimum number of electrons, but F isn't that important right now in our syllabus. Now, minimum number of electrons in subshell depends on the atomic number or the availability of electrons. So for example, if there are less electrons available, so in the S subshell, there could be 1 electron. In the P subshell, there could be 1 till 5 electrons. And in the D subshell, there could be 1 till 9 electrons. So now we'll apply this to write the electronic configurations of number of elements. So for example, sodium which has atomic number 11. The atomic number represents the number of electrons. So that means sodium has 11 electrons. So the first subshell, that is 1s, will have 2 electrons. The second will have, which is 2s, will have 2 electrons. So that makes 4. Now 2p will have 6 electrons. So 2 plus 2 plus 6 is 10. Now 1 electron remains. So that 1 electron will be in 3s, which will be 3s1. So this is how we write the electronic configuration. And if we want to relate this with O levels, so we can see that in the first shell, there are 2 electrons. In the second one, there are 8. And in the third one, there is 1. And this is the electronic configuration that we learned in O levels, that is 2, 8, 1. Now for example, oxygen has atomic number 8, that is 8 electrons. So 1s2, 2s2, 4 electrons have already been filled, so 4 electrons remain. So 2p will have only 4 electrons. Again, relating it to O levels, the first shell has 2 electrons, the second shell has 6 electrons. So the configuration would be 2, 6, as we did earlier in O levels. Now over here, we can see that the valence electron of any element represents group number. So the valence electron is represented by, just a second, the electrons in the valence shell. The valence shell is the last shell, the outermost shell. So in sodium, the valence shell is 3s, and it has 1 electron. So that means that sodium is from group 1. Similarly, for oxygen, the valence shell is 2. It has total 6 electrons. So that means that oxygen is from group 16. In A levels, from group 3 till group 8 are not called 3, 4, 5, 6, 7, and 8, but they're called 13, 14, 15, 16, 17, and 18. So oxygen, as it has 6 electrons in its outermost shell, is from group 16. Now, the principal quantum number represents the period number. We learned in O levels that the number of shells represent the period numbers. Over here, principal quantum number represents the number of shells. For example, in sodium, the principal quantum number, the highest principal quantum number is 3. So that represents 3 subshells. That means it's in the third period. Oxygen has 2 principal quantum numbers. That means that oxygen is in the second period. So just like this, we have to know how to write the electronic configuration for all non-transition elements from 1 till 20, that is from hydrogen to calcium. So also there is a shorthand method of writing the electronic configuration, that is the use of group 18 elements. For example, if we have calcium has atomic number 20. So it has electronic configuration as 1s2, 2s2, 2p6, 3s2. These add up to 2 plus 2 is 4, 4 plus 6 is 10, 10 plus 2 is 12, and then there is 3p6 and 4s2. After 3p, 4s comes because the energy of 4s is less than 3d, as we did earlier. So over here, we can see that these subshells have 18 electrons, and 18 electrons are contained in argon, which is a group 18 element. Argon's configuration is the same as the first 5 subshells of calcium. So in place of these 5 subshells, we can write argon 18, make a square bracket, and then the rest of the configuration. This is how we can simplify the configuration. Similarly, if we had sodium, in sodium, the first 3 subshells have 10 electrons. 10 electrons are contained in neon. So this can be replaced by neon. We can write it as Ne10, make the square bracket, and then the rest, that is 3s1. So therefore we can conclude that if we have more than 10 electrons, then we will use neon to write the shorthand configuration. If we have more than 18 electrons, then we'll use argon to write the shorthand configuration. These are the only 2 possibilities. Other group 18 elements cannot be used. Now for a few more examples. So for example, if we have phosphorus has atomic number 15, that means 15 electrons. So the full configuration would be 1s2, 2s2, 2p6, 3s2, and how many electrons remain? So 2 plus 2 is 4, 4 plus 6 is 10, 10 plus 2 is 12. So 15 minus 12, 3 remain. So 3p will have 3 electrons. Now, if we had to write this in the shorthand method, we could use neon over here because it has more than 10 electrons. So because phosphorus has more than 10 electrons, so you can write or. We'll replace the first 3 subshells with neon, and then 3s2 and 3p3. Similarly, if we have chlorine has atomic number 17. The full configuration would be 1s2, 2s2, 2p6, 3s2, and 3p. Now for this, 2 plus 2 is 4, 4 plus 6 is 10, 10 plus 2 is 12. So 17 minus 2 means 5, 5 electrons remain, so 3p5. Now over here again, we could replace these 3 subshells with neon and then write 3s2 and 3p5 after that. Now, how do we write the configuration for ions? For example, if we have a sodium ion, sodium has 11 electrons. So if it's a sodium plus 1 ion, that means it has lost 1 electron. So it will have 10 electrons. So over here we'll have 1s2, 2s2, and then 2p6. So we've left out the 3s1 that we used to have in the full configuration of sodium atom, and we have 1s2, 2s2, and 2p6, that is 10 electrons. Similarly, if we had oxide ion, oxygen has atomic number 8. If it loses 2 electrons, if it gains 2 electrons to get the -2 charge, so it will have 10 electrons. So again, the configuration would be 2s2 and then 2p6. Over here, we'll also do fluorine. Fluorine has a -1 charge and atomic number 9. So its configuration would also have 10 electrons because it has gained 1 electron. So 9 plus 1 is 10. So it will have the same configuration. Now over here, as these are 2 anions, at its negative ions and have the same configuration. So they are called isoelectronic anions. Now, one more thing that we'll do over here is the valence configuration for non-transition elements. From the examples that we've done, we can see that the valence electron for group 1, the valence shell of group 1 atoms has the S1 subshell, which with the period number before that. For example, sodium has S1 and the period number is 3, so it's 3S1. Oxygen is in group 16, so it has S2 and P4, and then it's in the second period, so it has 2S2, 2P4. So in general, if we had to write the valence configuration, means the configuration of the valence shell, that is the outermost shell. So for group 1, it would be S1, 2, I'm just picking them up randomly. So for 2, it would be S2. For 4, it would be S2, P2, so that there are 4 electrons in the outermost shell. For 6, it would be S2, P4. And then 7, it would be S2, P5. Now, for example, if we had chlorine, which is in the third period, and in group 17, we'll have group 14, 16, and 17. So if there was chlorine from group 17 and period 3, so we could directly write its valence configuration as 3s2 and 3p5. Or if we had from group 16 sulfur is also in the third period, so its configuration would be 3s2 and then 3p4. If we had calcium, which is in the fourth period, then and the second group, so its configuration would be 4s2. I hope that's clear. Next is the configuration of transition elements. In transition elements, there is an exception to the order of the orbitals. From 1s to 3p, it is the same order, that is 1s, then 2s, then 2p, then 3s, then 3p. But after 3p, normally comes 4s according to the energy level. But over here, first 3d is there, and then we write 4s. Even though we fill 4s first, but we write 4s afterwards. The reasons for this are that the reason for this is that the 3d and 4s orbital have a very close energy. Their energies are very close. That's why they overlap, and that's why we write 3d first. However, electrons are first filled in 4s, and when electrons are being lost, electrons are first lost also from 4s. Now, in transition elements, the elements that are in our syllabus are from atomic number 21 to 30. Those are scandium to zinc. Now, we'll do some examples. So, first, there is scandium. Scandium has atomic number 21. So that means 21 electrons. So first we have 1s2, 2s2, 2p6, 3s2, then 3d, and 4s. First we'll fill 4s, then we'll count how many electrons have been filled. Sorry, I missed 3p. 3p6. Then we'll write 3d, but we'll first fill 4s. Now counting how many electrons have been filled. So 2 plus 2 is 4, 6, 10, then 12, 18, and 20. 20 have been filled, and out of 21, 1 remains. So 3D will have 1. Similarly, the next element we can take is, for example, vanadium. That is V23 is its atomic number. So over here, the configuration will be 1s2, 2s2, 2p6, 3s2, 3p6. We'll first write 3d, but we'll first fill 4s. So this means that there are 2 plus 2, 10, 18, 20 electrons, and then 3 remain. So 3d will have 3 as its number of electrons. Now over here, again, we can also use shorthand configuration. So for example, from 1s till 3p, there are 18 electrons. So we can replace this by argon 18 and then write 3d3 and 4s2. Next example I'll take is zinc. Zinc has atomic number 30. That means 30 electrons. So its configuration will be 1s2, 2s2, 2p6, 3s2, 3p6. We'll first write 3d, but we'll first fill 4s. Now counting electrons, there are 20 electrons, 10 remain, so 3d will have 10. Now in transition elements, there are 2 exceptions. The exceptions are in chromium and in copper. So first chromium is Cr, atomic number is 24. If you follow the same pattern of writing the configuration for chromium, it would be 1s2, 2s2, 2p6, 3s2, 3p6, write 3d first, fill 4s first, and then 10 electrons, 20 electrons have been filled, so 4 remain, so 3d will have 4. However, in chromium, what happens is that 1 electron jumps from the 4s orbital into the 3d orbital. So the correct configuration for chromium is 1s2, 2s2, 2p6, 3s2, 3p6. 3d has 5 electrons and 4s has 1 electron. So this is the correct configuration. And then for copper, which also has an exception, it has atomic number 29. Over here, the configuration would be 1s2, 2s2, 2p6, 3s2, 3p6, 3d. We'll first fill 4s. 9 electrons remain, so 3d will have 9. Now again over here, 1 electron is transferred from 4s to 3d orbital. So the correct configuration is 3d is 10 and 4s is 1. So this is the correct configuration. Now the reasons why this happens. is because chromium and copper get more stability in this arrangement. What is the criteria for stability? An element is stable if its orbital is full or its orbital is half. In both these cases, it is stable. So to get stable, one electron can be transferred from one orbital to the other, but this will only happen if after this transfer of electrons, all the orbitals are either full-filled or half-filled. Now to explain this, over here, in the first case, the 3D orbital is neither half-filled nor full-filled. And to get stability, one electron can be moved from one orbital to the next. And it's always from a higher energy orbital to a lower energy orbital. Sorry, from a lower energy orbital to a higher energy orbital, because 4s is lower energy, as we did earlier when we used Aufbau's principle, n plus L rule. Over there, we determined that 4s has lower energy. So transfer of electron always occurs from lower energy orbital to higher energy orbital. So it will always occur from 4s to 3d. Over here, if an electron is transferred from 4s to 3d, 3d would not gain stability. So that's why over here, this transfer does not take place. Similarly, in vanadium, if one electron is transferred, 3d would have 4 electrons and 4s would have 1 electron. 4s would still be stable, but 3d would not get stability. So again, over here, it does not happen. In zinc, so all of it is stable, so there's no need. In chromium, we can see that 3d originally is not stable. Chromium is not stable because 3d is not half-filled or full-filled. However, if one electron is transferred from 4s to 3d, we can see that even 3d will get half-filled and 4s will get half-filled, which means chromium will get stable. Similarly, in copper, when one electron is transferred from 4s to 3d, 3d will have 10 electrons, 4s will have 1 electron, 3d is full-filled, 4s is half-filled. That means copper is stable. So that's why this only happens in chromium and copper, that an electron is transferred from 4s to 3d, that is from a low energy orbital to a high energy orbital, to get stability. Now, ions of transition elements. I'll give one example of iron. For example, iron 2 plus and iron 3 plus ions. Iron's atomic number is 26. So if it has 2 plus charge, that means it has lost 2 electrons. So its electrons will be 24. So for that, the configuration will be 1s2, 2s2, 2p6, 3s2, 3p6. First, I'm writing the general configuration of the iron atom, which is 3d, then 4s2, 6 electrons remain, so 6 over here. Now, 2 electrons are being lost, and we did earlier that electrons are always lost. Electrons are always lost first from the 4s orbital. So first, the 2 electrons from 4s will be lost. So the configuration of iron 2 plus will be without the 4s orbital, that is 1s2, 2s2, 2p6, 3s2, 3p6, and 3d6. For the iron 3 plus ion, there are 3 electrons lost. So that means that after 2 electrons are lost from the 4s orbital, one will also be lost from the 3d orbital. So the configuration will be 1s2, 2s2, 2p6, 3s2, and 3p6, and 3d, 5. Next is spin configuration. So according to spin, this topic tells us that electrons are also called spins, and spins are represented by an arrow, which can either be like this, or it can also be like this, like a half arrow or a full arrow. So there are two types of spins. One is the upward spin and the downward spin. Now, to find the direction of movement of the spin, we use the right-hand grip rule that we did in O-level physics. So our thumb points in the direction of the arrow, and the direction of our curved fingers shows us the direction of the direction of the rotation of the spin. So the upward spin has an anti-clockwise rotation, and the downward spin has a clockwise rotation. Now, if you have a single electron, or an unpaired electron, that is shown as this or this. But if we have a paired electron or a paired spin, it is shown either as this or as this. Now next is the boxes that we show when we are doing the spin configuration. So the first subshell, that is S, has one orbital as we did earlier. So it has one box. Each box represents one orbital. The P subshell has 3 orbitals. It has 3 boxes. We can label them as Px, Py, and Pz. Px, Py, and Pz. And then the third one, that is T subshell, has 5 boxes for its 5 orbitals. Now we need to remember that when we're filling in a subshell, we'll first fill an electron in each orbital. We'll first fill one electron in each orbital, the upward spin, and then after all the orbitals of that subshell have one electron, then we'll start filling another electron in each orbital. So, for example, we'll take oxygen. Oxygen has atomic number 8, so 8 electrons. So it has configuration as 1s2, 2s2, 2p4. So for the 1s subshell, we'll make one box. For the 2s subshell, we'll make another box. For the 2p subshell, we'll make 3 boxes joined together. First, we'll fill 1s. First, fill one electron, then another. Then in 2s, one electron, then another. In 2p, first we'll fill one electron in each orbital. But first we filled one electron in each orbital. Now we'll start filling the next electron in each orbital. But we have only 4 electrons, so the last 2 orbitals will have only 1 electron. Now these 3 are called paired electrons or paired spins, and these are single or unpaired. Next example is of iron. Iron has atomic number 26. So its configuration would be 1s2, 2s2, 2p6, 3s2, 3p6. Then we'll write 3d, then we'll write 4s2. 6 electrons remain, so 3d will have 6. Now the boxes that we'll make, first for 1s, we'll have one box. For 2s, we'll have one box. For 2p, we'll have 3 boxes joined together. For 3s, we'll have one box. For 3p, again 3 boxes. For 3d, we'll have 5 boxes. And for 4s, I'm drawing it over here, 1 box. Now filling them, first we'll fill 1s fully, then 2s. In 2p, first we'll fill 1 electron in each box, and then another one. And in 3p again, we'll fill 1 electron in each box, and then we'll fill the downward spin in each. Now in 3d, we'll first fill 1 electron in each box. Then 1 remains, so we'll fill that in the first one. In 4s, there will be 2 electrons. If we wanted to write this configuration in the shorthand method, so what we could do is we would write argon 18 and then only write the 3d and 4s subshell. So that would be like first filling singly and then the second one. So this would be the shorthand configuration. Both are correct. The method that we were using in the last 2 examples, the horizontal method, this is for P1s. However, in P2s, we do the configuration in a vertical manner. That is, for example, if we have nitrogen with atomic number 7, we'll first draw an arrow and label it as energy. So that means that going upwards, energy is increasing. The lowest energy is of 1s, then 2s, and highest is of 2p in this configuration. 1s has 1 box, 2s has 1 box, and 2p has 3 boxes. First, we'll fill 1s, then we'll fill 2s. Now we have filled 4 electrons, 3 remain, so we'll fill them singly in 2p. So this vertical configuration is for P2s. If we had to give the valence configuration in terms of spins, so we could just see the valence shell and then give the configuration of that. For example, if we have calcium, calcium's valence shell is the 4th shell, and that has configuration 4s2. So the valence configuration for calcium would be directly, sorry, there will be only 1 box, and we'll fill the electrons. This is for calcium, or this is the valence configuration for any element in group 2. Similarly, if it was group 15, for example, nitrogen, then its valence shell would be 2s2 and 2p6, or sorry, 2p3, 2s2 and 2p3. So we'll write that in spin form. First 1 box for 2s and then 3 boxes for 2p. So first fill 2s and then 2p. So this would be the valence configuration for any element of group 15. If we had group 18, for example, argon's valence shell is 3s2 and 3p6. So its valence configuration in terms of spins would be so the valence configuration for any element of group 18 will be this. Now, what is ground state and excited state? What happens is that when we provide energy to an element, an electron is transferred from a low energy orbital to a high energy orbital. So that brings the element into its excited state. Otherwise, it's always in its ground state. So the normal element. For example, if we have carbon 6, atomic number is 6, its electronic configuration would be 1s2, 2s2, and 2p2. So if we make this in terms of spin, we have one box here, and 3 here. This would be the electronic configuration. And now what happens is that when we provide energy, the electron is transferred from the lower energy orbital to the higher energy orbital. Sorry, from the lower energy orbital to the higher energy orbital. So this electron is transferred over here. Now the electronic configuration for carbon would be electron is transferred from here. So this has 3 electrons now. So when the element is in its excited state, it has one, like it has for carbon, the 2s orbital has one less electron from its normal ground state. Now, why does this happen? We know that there are two spins, the upward spin and the downward spin. The upward spin has a rotation that is anti-clockwise, and the downward spin has a rotation of clockwise. The upward spin has high energy, and the downward spin has low energy. Now, if, for example, we have an orbital and infrared energy is provided, so the upward spin would remain the same. However, the downward spin would gain energy and would become an upward spin. Now, because the direction of its rotation becomes the same, they will experience repulsion, and one of the electron is transferred to a higher energy orbital. I'll give another example because this is a little confusing. So for example, if we have, instead of carbon, so instead of carbon, we have, for example, oxygen. Oxygen's electronic configuration I'm doing in terms of spins. So there is the first 1s, then 2s, and then 2p. So there are 8 electrons. So when we start filling them, now when we provide, this is the ground state. This is the ground state of oxygen. But when we provide energy to this, what will happen is that an electron will be transferred from a lower energy orbital to a higher energy orbital. 2s is a lower energy orbital. So one electron is transferred from here. Sorry, I made a mistake in the configuration. There will be one downward spin over here to complete the 8 electrons. So one electron is transferred from here to there. And the excited state configuration will therefore be (2s) will have only one electron, and 2p will have 5 electrons now. What was happening over here was that when we provided energy, this downward spin became an upward spin. Therefore, the two spins experienced repulsion, and this one was transferred to the 2p subshell, just shown over here. The next topic is the shapes of orbitals. The s orbital or the s subshell, which has only one orbital, is spherical in shape with a dot in the middle. Now the difference between the 1s, 2s, 3s, and 4s orbitals is if, for example, this is 1s, this is 2s, this is 3s, and this is 4s. So all of them are spherical, just the size increases. Next is the p orbital or the p subshell. So the p subshell. Now, in general, the p subshell has a dumbbell shape or infinity shaped shape. However, there are differences in the orbitals, but generally we'll just show them as a dumbbell shape. And again, what's the difference between 2p, 3p, and 4p? So 2p will be, for example, like this, and 3p will be like this, and then 4p would be. So again, in 2p, 3p, and 4p, the difference is only of the size. Over here in the p subshell, we have three orbitals that are px, py, and pz. So px, py, and pz. Now there is a difference between these three, and we will show them if we are asked about the specific orbitals. However, in general, we'll just show it in this manner. So if it is px, then it is the same, that is horizontal. However, if it is py, then it is vertical. And if it is pz, then we'll draw this line and it will be in this manner. The third subshell, that is the d subshell. The d subshell is in the shape of a double dumbbell or double infinity shape. So we can show it as this. Over here, we don't need the shapes of the specific orbitals. This is all that is included in our syllabus. And for F subshell, even though it's not included in the syllabus, but I'll just give the name of the shape. The F orbital is leaf shaped. That's all for this video. In the next video, we have some more parts of this topic that are ionization energy and deflection of subatomic particles.